Hello, everyone. Welcome to this Advanced Materials Forum Europe. We are excited. I'm happy that you're all on board for this virtual forum event. Due to the corona restrictions, we decided to host the online forum sessions from our home offices. So we don't have a physical interaction, but we do all this, let's say, remote. If you have any questions during this session, you can submit the questions via the chat function, and we will answer your questions as soon as possible. Okay, let's first introduce myself. My name is Alexander Stroeks. I'm a principal scientist at the DSM Material Science Center. And what I would like to discuss with you today is the topic of polymer materials, enabling hydrogen as a safe and reliable energy source for automotive. And as you can see, I give this presentation, but you see that there are other people on the list who also contribute to this particular activity. Okay, the outline of my presentation today. First, I would like to discuss with you on a somewhat general basis, why is hydrogen suitable as energy carriers? And I also want to make a bit of a comparison how hydrogen as energy carrier relates to other types of fuel. Then I would like to go in somewhat more detail in certain applications that we are looking at, applications that are related to hydrogen as energy source for automotive applications. The first application I would like to discuss with you is related to high pressure hydrogen tanks. These tanks consist of a polymer-based inner liner for gas barrier purposes. That's something I would like to discuss with you rather extensively. Also, I would like to discuss composite tape wrapping for the mechanical strength of these tanks, where we are looking into. So that are the topics related to tank applications. I also want to spend some words on the work that we are doing on polymer materials for fuel cell applications. And then, of course, I want to end up with some conclusions. Okay, so first let's take a bit of a step back and look what are the roles of hydrogen in decarbonizing our economy. As you see here from this particular graph, you see that when you look at for instance, the energy generation in Europe, that more and more sustainable energy takes over from fossil energy. And then you have to think about wind energy, solar energy. But when this contribution increases, I think there is an increased demand for buffering the energy that you generate, because in times when there is no sun, no wind, you still need this energy supply. So there is a huge demand in buffering. Now you can buffer energy in different ways, but I think hydrogen is a very good way of buffering your electric energy in this case. So that's one important element in this transition towards a hydrogen-based economy, let's say. When you look at end users for hydrogen, there are different segments that we can identify. Of course, an important one is the area of transport. And that is the topic that I would like to discuss with you today. But of course, there are also areas related to industry, where hydrogen is used as energy source, to fuel certain plants, for instance, or certain factories. That is an important element. Of course, hydrogen classically is used as feedstock. And also it will help to decarbonize, for instance, building heating, replacement of fossil-based systems for building heating. But today, I would like to focus on the transport applications. Well, I think this is a rather interesting graph. This is a graph from the Hydrogen Council. And what you see here basically is the following. Yeah? Here you see different types of vehicles, yeah? So-called BEV vehicles in light blue, battery electric cars. Then we have fuel cell electric vehicles, yeah, in the middle part of this graph. Yeah, when I speak about fuel cell electric vehicles, I mean vehicles that at the end are powered by hydrogen. Yeah? And then we have an area in dark green in this graph, where we speak about vehicles that will be powered by, for instance, bio or synthetic fuels. Well, what are the vehicles that we mean? When you look at the axis, on the x-axis we have the mileage per day. So short mileage, 10 miles, small vehicles, large mileage. Then we speak about, for instance, aeroplanes or ships. On the y-axis, you have the weight of the vehicle, varying from something like 0.1 ton to thousands of tons. Well, when you think about the most suitable fuel for these types of vehicles, I think there is quite a consensus about the different areas. For instance, when we look at this light blue area, we speak about small vehicles, small cars, urban mobility. I think there is consensus that these vehicles will be powered by batteries. So that's one, let's say, extreme area. The other extreme area, you could say, are formed by these very heavy vehicles like planes, aviation. For aviation, batteries, but also hydrogen tanks and fuel cells, they are not suitable for aviation purposes. And the reason mainly is that the weight of the battery, also the power of the fuel cells, is insufficient for these types of applications. So I think there is consensus that planes will be powered by synthetic fuels. But there is a mid-regime in this graph where you see, for instance, buses or trucks or trains. And there the assumption is that in the future, that these systems will be powered by hydrogen. And I think there are good reasons for that. And also here, I think there is a type of consensus. Now, an interesting area is, let's say, the area of personal vehicles, medium to large cars, for instance, fleets and taxis. And there, the question is at the end, in the future, what will be the most favorable energy source? And I think there is quite a debate about this. Some arguments, they go in favor for battery electric propulsion. There are also people who think that it might be hydrogen. There are also already commercial examples, as you know, Toyota, Hyundai, that commercialize hydrogen-powered cars. So this is still a debate. Will it at the end be powered by battery, this particular segment, or will it mainly be powered by hydrogen? And I think that's an interesting discussion. Okay, when you look at the strategic fit, what can we, let's say, bring as DSM, as a material company, to this whole discussion, and also to this hydrogen-powered vehicles? I think we have competences in place. We have also material in place where we can play an important role with respect to the high pressure hydrogen tanks, but also for the fuel cell components that you need. And later on, I will discuss these materials in somewhat more detail. Okay, when you look at a high pressure hydrogen driven car, this is an example. This is an example of a Toyota Mirai, and there you can distinguish, let's say, different elements. Obviously, a very important element is the high pressure tank, where you basically store hydrogen in a kind of gas or supercritical form at 700 bars, which is quite a high pressure. That's one important element, the high pressure hydrogen tank, where we think as DSM we can contribute. But you also have the fuel cell stack. The main purpose of the fuel cell is to convert the chemical energy of the hydrogen into electrical energy. And this electrical energy then powers the electromotor to propel the car. Also in this fuel cell stack system, we think, based on our material position, that we can contribute. Okay, when you think about hydrogen as energy carrier, how does it relate, let's say, to other forms of fuel, or energy carriers? And in this graph, what you see here is basically a graph of energy density, expressed in two ways. And when you look at the x-axis, you see the gravimetric energy density, so the energy density based on mass. And on the y-axis, you see the same energy density, but then expressed per volume, so per liter. And what you immediately see from this graph is that when you look at hydrogen, in the right bottom part of this graph, you see that the gravimetric energy density is extremely high. Something like a factor 4 higher compared to the classical fossil-based fuels like diesel or gasoline or kerosene. So that means that to have a same amount of energy, you need much less weight. It's about a factor 4 or a factor 5 difference. Especially when you compare it to battery systems. On the left bottom part of this graph, you see, for instance, lithium-ion battery. On a weight basis, they don't compare very well. And you need a lot of weight to get a similar amount of energy. So on a mass basis, liquid has a very high energy density. On the other hand, when you compare it based on volume, then you see a different picture. When you look at the y-axis, energy density per volume, you see that the fossil-based systems, they are better. They express more energy per volume. So you need less volume to store the same amount of energy compared to hydrogen. But certainly when you compare it to, for instance, lithium-ion batteries. So that means when you want a amount of energy to drive your car, in volume, you need much more than based on, for instance, petrol. But on mass, you need much less. That's the message that you get from this picture. And in the next graph, basically, I expressed the same numbers for different energy storage materials. And what you see here is an overview of the different energy sources where you make use of chemical energy. That's the second column. Here you see the word chemical. You also see the word electrochemical. So when you speak about batteries, they are in the bottom part of this particular table. But you also can make a comparison related to, for instance, nuclear type of materials. I did that more for a joke. For instance, when you look at a system like, for instance, uranium, you see that the energy density is much, much higher, many, many decades higher compared to, for instance, hydrogen or to gasoline. The consequences I will discuss later. Okay, when you think about hydrogen as energy carrier, you can store hydrogen in different ways. You can store it as a gas, you can store it as a liquid, and you can store it in combination with a solid, where you rely on, for instance, absorption or adsorption type of mechanisms. When you want to store hydrogen as a gas, you really have to go to high pressures. Yeah, else you need too much volume to store your system. Yeah. So what happens in practice, that gas often is stored under 700 bars of pressure, which is quite high. Yeah. And that gas for these high pressures is stored in these compressed hydrogen tanks. Yeah. I will discuss in detail later. You also can store hydrogen as a liquid, but then you have to go to extreme low temperatures, cryogenic conditions. Here in this bottom part, you see the phase diagram of hydrogen. Yeah, so to exist as a liquid, yeah, hydrogen must be cooled to something like 33 Kelvin, because that is the critical point of hydrogen. So really, really low. Yeah, when you want to store hydrogen in a liquid state at atmospheric pressure, yeah, it needs to be cooled to something like 20 Kelvin. Yeah, so very close to the absolute zero in temperature. Yeah, so extreme low temperatures. It is being done. There are practical examples, but you have to realize that the temperatures that you need are extremely, extremely low. Okay, then you can store hydrogen also in combination with solid materials. Yeah, there are examples described where people use carbon-based materials or these metal organic frameworks, where you allow hydrogen storage in, for instance, these open systems. You have vacancies or open places in your material where the hydrogen will be absorbed. Also, polymers are mentioned, polymers that have a high porous structure where hydrogen could reside. Yeah, so these are the examples of systems that you could use to store hydrogen. But as far as I know, there is a lot of scientific literature about these storage methods, but I am not aware of commercial applications. Yeah, it's mostly discussed in academia. Yeah, but when you look at industrial applications, I think it is rather limited. Yeah, so from industrial point of view, the liquid, but especially the gas-based systems, that's what you see happening in practice. Okay, let's look a bit at the amount of energy that you need to get a certain driving range of a car, yeah, and also the amount in weight that you need to get this driving range. Yeah, and I try to make some estimates about this. Yeah, and I'm sure that in the audience there are people that know much more about this type of estimates than I did. But I think when I did this, let's say at the back of an envelope calculation, I think it's still pretty close to reality. Well, let me guide you through. Imagine I have a car, yeah, a fuel-based car, with a fuel consumption, let's say 1 liter on 15 kilometers. Yeah, then for a 600 kilometer driving range, I need something like 40 liters of fuel. When you look at gasoline, yeah, it has a certain energy density, yeah, about 34 megajoules per liter. Yeah. You also know the combustion engine efficiency of your engine, which is about 28%. I took, maybe it's somewhat higher, but okay, let's for the time being, let's take this efficiency number. Yeah. Then you can calculate back that when you have 100% efficiency, yeah, you need something like almost 400 megajoules of energy, yeah, to get a driving range of something like 600 kilometers. Yeah. This is what you expect based on this estimate for a fossil-based fueled car. This is for 100% efficiency, right? Now, when you look at the efficiency, yeah, of, for instance, a battery electric car, yeah, that you see on the left part of this graph, yeah, then for a battery, a lithium-ion battery car, yeah, the energy efficiency is pretty high. Yeah. When you look at the tank-to-wheel efficiency, it is about 77%, which is really high. You have some losses related to the inversion from AC to DC and vice versa. You have some losses with respect to the electric engines that are being used. But overall, an energy efficiency of something like 77% can be reached, which is pretty high. Now, for hydrogen-powered cars, where you have a fuel cell-based system, the situation is very different. When you look at the right-hand part of this graph, you see that the tank-to-wheel efficiency for a fuel cell-based car is only 42%. And the largest energy, let's say, loss that you have is related to this fuel cell, where you convert electricity, where you convert chemical energy back to electrical energy. And there you have about 50% of energy loss. So you have to realize that the fuel cell is not very energetic efficient. And something like half of the amount of energy of the hydrogen that goes in is released into heat, and half is released into electrical energy that you need to propel your car. So when you compare these two types of systems, battery versus fuel cell, a battery car is much more efficient. Okay, now let's have a look what this means for the weight of fuel or the weight of battery that you need to get to this 600 kilometers driving range. And here I made a kind of overview where I made these estimates. When you look at the energy density of hydrogen, and when you do the calculation based on this rather low tank-to-wheel energy efficiency, you end up at something like 6.4 kilograms of hydrogen that you need to get this driving range. So on a weight basis, you only need something like 6 kilograms to get the driving range of 600 kilometers, which is not a lot on a weight basis. On the other hand, when you do the same calculation for a lithium-ion battery, despite the fact that you have a very high tank-to-wheel efficiency, something like 77%, because of the fact that the energy density on a weight basis for a battery is pretty low, you come to the conclusion that the amount of lithium-ion battery that you need is something like 560 kilograms. So that's much, much more compared to the amount of hydrogen that you need. And for fun, I also included uranium. Uranium I showed you before, energy density extremely high. To get a driving range of 600 kilometers, you only need 0.01 gram of uranium. So when you want to drive 100,000 kilometers, you only need 1.8 gram. So these systems are much more energy efficient, but of course not that realistic. Now, how does this compare to the practical information that I found? Well, when you look at this, for instance, this Toyota Mirai, the tanks, they carry about 5 kilograms of hydrogen, which is very close to the theoretical estimate that I showed you before. For the lithium-ion battery, when you look at, for instance, the Tesla S system, you have a total battery weight of something like 540 kilograms, which is also pretty close to these theoretical estimates. Uranium-based car, that's not commercial yet. But this is about the amount of fuel that you need. But of course, there is more than only the fuel. When you look at the hydrogen-powered car, of course, you also need a hydrogen tank with a certain weight. You need a fuel cell with a certain weight. And you still need a small battery on board. When I look at the values, for instance, for this Toyota Mirai, it means that, for instance, the hydrogen tank, it weighs about 87 kilograms. Yeah, the fuel cell, it weighs about 56 kilograms. When you add up these numbers, yeah, even without the small battery that you need, yeah, you need more than 150 kilograms, yeah, to get the whole system for the hydrogen infrastructure in place. That's still much less compared to the lithium-ion batteries, but that is something that you have to realize. Yeah, but still, on a weight basis, a hydrogen-powered car, yeah, you need much less weight to have the hydrogen infrastructure in your car compared to the battery infrastructure. So that's clearly an advantage of hydrogen-powered cars. For the specific German situation, yeah, there is this interesting report from the Jülich Forschungszentrum, yeah, and they basically investigated the consequences for the infrastructure. Yeah, and they made, I think, a very interesting comparison. And when you look at this particular slide, in the left graph, what you see basically is the investment costs, yeah, that you need to develop an infrastructure, yeah, for fuel cell electric vehicles and for battery electric vehicles. Yeah, so on the y-axis, you have the investment that you need, and on the x-axis, that's basically the amount of electric powered cars, either battery or fuel cell. Yeah? What you see from this graph is that for low volumes of cars, yeah, in the order of a few million, yeah, the investment in a battery-related infrastructure, yeah, is lower compared to the investment in fuel cell infrastructure. Yeah? But from a certain amount of vehicles, yeah, somewhere around 10 to 15 million vehicles, yeah, the amount of investment in the infrastructure is almost the same. But when you go to high amounts of cars, yeah, you see that the investment for the hydrogen infrastructure is even lower compared to battery electric vehicles. Yeah, so some people have this idea when you go for hydrogen powered cars, you need this investment in pipelines and refueling stations, yeah, which is huge. But when you look at this study, for high amount of cars, yeah, the situation is the opposite. It's cheaper to invest in this infrastructure for hydrogen compared to, let's say, the electricity infrastructure for battery powered cars. Yeah? Okay, that was a bit a discussion so far, a more general discussion about hydrogen and its role in this hydrogen-based economy and its role for transport applications. But now let's look at some more concrete applications. Yeah? Let's look at, for instance, hydrogen fuel tanks. Yeah? Here you see an example from a Toyota Mirai brochure. And there are some, let's say, important elements here. You can imagine that the hydrogen permeation of this tank plays a very important role. You don't want too much hydrogen to migrate to the outside world. So the permeation characteristics of the tank are important. You also need good mechanical performance of your tank. Yeah, the weight should not be that high. So these are all, let's say, elements that you have to consider when you want to develop such a fuel tank. Now, in this graph, you see the evolution in tank development. When you go back in time, most of the tanks that were being used, yeah, they were classically made out of steel, out of metal. Yeah, and what you see is when, let's say, the tank generations proceed, you see a replacement of metal by polymer-based materials. And the most important driver here is weight reduction. Yeah. Well, now, in this time, we have arrived at type 4 tank applications. Type 4, that's the generation we are in. And what does that mean, a type 4 tank? When you carefully look at a type 4 tank, you see different elements. The first element is a kind of inner liner, a cylinder on the right part of this graph, a polymer-based inner liner. And the main purpose of this inner liner is to get sufficient gas barrier. That's one important element. The other important element is that this inner liner is reinforced by a kind of composite wrap around this inner liner. And that should provide sufficient mechanical strength, because you need to withstand the 700 bars of hydrogen. So for this type 4 tank, what you see a split of these two very important functionalities. Well, typically, when you look at such a tank, it contains 5 kilograms of hydrogen. That is one example. For instance, for the Toyota Mirai, where you need to carry 5 kilograms of hydrogen, you have 2 or 3 smaller tanks. But let's take this example, one tank carrying 5 kilograms of hydrogen. When you take into account the density at this high pressure, it means that the tank volume is around 120 liters. That is the total volume that you end up with, which is larger than the volumes to start, for instance, petrol. That relates to this energy density on a volumetric basis, right? That we discussed before. So you need larger tank volumes to store the same amount of energy compared to classical fuel. Okay, when you look at these tanks, there are hydrogen permeation requirements in place. And currently there is a requirement that the permeation of hydrogen through the outside world should not be higher than something like 6 normalized cubic centimeters per hour and per internal tank volume. So per liter of internal tank volume. And with normal cubic centimeters, I mean the gas volume of the hydrogen under standard conditions, being room temperature and 1 atmosphere. So this is the requirement for the permeation that is in place at this moment. And we are at DSM developing materials that comply with these permeation values. And this development, you could say, this relies on permeation expertise at DSM that we developed over the years, because this is not the first topic where we deal with permeation questions. Basically, we started with doing permeation experiments already quite a while ago, because DSM is also involved in, for instance, polymer filler materials that are used for food packaging, where also gas permeation plays an important role, oxygen, CO2, water permeation. So we built already expertise long time ago related to these types of applications. We also developed several years ago already fuel tanks for gasoline. And here you see an example of a relative small gasoline tank that is used for these lawn and garden equipments. So we have solid expertise in place that we can nicely use now to develop materials that could serve as these inner liner materials for hydrogen tanks. Well, here you see an example. When you look at different materials, how do the hydrogen permeation values relate to each other? At DSM, we address this hydrogen permeation issue based on polyamide materials, because we have rather solid polyamide material position at DSM. When you take a polyamide example and you put this hydrogen permeation value at an arbitrary value of 1, then you can make comparisons with other type of polymer materials. And what you see basically is that these polyamide materials are pretty okay. They have low permeation values when you compare them with PET, with PEEK, with polyamide 11, yeah, or HDPE, or even polycarbonate, you see that the permeation of these polyamides is really low. And when you look in literature or in other studies, this is an example of a Sandia study of a few years ago. Yeah, you see that only POM, for instance, polyoxymethylene, yeah, is somewhat better compared to our polyamide systems because it even has a lower permeation value. Yeah. Also EVOH, so a copolymer of ethylene and vinyl alcohol, also shows rather low permeation values, but these materials you cannot use as a single material. You always have to go to multi-layer type of applications for EVOH. Yeah? So we think that polyamide materials form a good starting position. Okay, what we did is that we started collaborating with a German test institute called TestNet. Yeah, they are located near Munich. And the reason for this collaboration is that at DSM, we don't have a license, a safety license basically, to handle hydrogen at 700 bar pressure. Yeah, there are only a limited amount of institutes in Europe or in the world. Yeah, and TestNet is one of them. Yeah, so we started collaborating with TestNet, and they have equipment to measure the permeation of hydrogen under these high pressures. Yeah, and the measurement basically is quite straightforward. What you do in this scheme, you have a sample given in green, for instance, a certain polymer plate with a certain thickness, typically a few millimeter, 2 millimeter or so. On one side of the plate, you apply a high pressure of hydrogen, 700 bars, for instance, and on the other side, on this lower side, you detect the amount of hydrogen gas that permeates through this polymer material. That's basically what you do. You detect the amount of hydrogen, the volume of the hydrogen gas as a function of time. And here you see an example of such an experiment. On the y-axis, you see the reduced permeability value, between 0 and 1. And on the x-axis, you see time. So basically what you do is that you start your experiment at time is 0, and then you see a gradual increase of the permeation over time. And when you wait long enough, you get a so-called steady state permeation value. The reason that you need some time to reach this is the fact that the hydrogen has to diffuse through the polymer material. And from this time that you need to get to the steady state value, you can extract a diffusion coefficient for hydrogen in our polymer material. So these are typically the measurements that we get. And from the interpretation of the measurements, you can get permeation values, diffusion values. And when you know these two, you even are able to calculate back a solubility value of the hydrogen in the polyamides material. And here you see an example of, for instance, a polyamide 6 based material. You measure a certain permeation value, something like 480 cubic centimeter per hour per square meter, which boils down to something like 1 gram per square meter per day, which is obviously not a lot. But you're also able to extract diffusion coefficient values. Diffusion coefficient is in the order of something like 30 times 10 minus 12 square meter per second, which is pretty fast compared to other gases, really fast. While the hydrogen solubility that you end up with is extremely low. Here, the solubility value is expressed in ppm. 1 ppm corresponds to 10 minus 4 weight percent. So you end up with a value of 340 ppm under 700 bars of hydrogen, which is extremely low compared to other gases. So diffusion speed, pretty high, solubility, very low. You see this in this graph. Here I compared the diffusion of hydrogen in relation to the diffusion of oxygen. And then you see that you come to the conclusion the diffusion speed of hydrogen is a factor 100 higher. So really, really high. Now, what is the underlying reason for this? That's something that we investigated at DSM. One reason could be that when you look at a polyamide, it is a semi-crystalline material. So you have crystals present. So could it be when you look at the size of the hydrogen, depicted here in blue, hydrogen is a much smaller molecule compared to an oxygen molecule, depicted here in green. So could it maybe that when you look at the crystalline structure, the crystals, for oxygen, we know that these crystals act as a kind of blockades. The oxygen cannot migrate through the crystals, but could it be that hydrogen is so small that it fits in the crystal and that it can move through the crystal? That's one way of explaining. The other way of explaining could be that besides the crystalline phase, you have the amorphous polyamide phase. Could it be that because of the fact that the size of the hydrogen is so small that it is able to migrate much faster? That was things that we are investigating. Also, the solubility question. I told you before that the solubility of hydrogen is much lower compared to oxygen. That's also a bit strange, because when you think about the amorphous phase, you could say that in this amorphous phase you have little holes, free volume pockets, and you could argue that when you have a gas that has a smaller molecular size, that it fits better. It fits even in these very small free volume pockets. And based on those arguments, you would expect that the solubility for the hydrogen is larger compared to oxygen, but you don't see that, it's lower. So what we did is, in order to try to get some answers to these more, let's say, fundamental questions, we did some modeling activities. At DSM, we have advanced modeling capabilities. Here you see an example, and basically what we did here is the following. We have computer models. With these computer models, you can construct a crystalline polyamide phase, as depicted in this graph. And then you can calculate basically the energy that it needs to position a hydrogen molecule in this crystal. You can calculate the energy it takes to put a hydrogen molecule in the crystal, and you can compare that with the energy of the hydrogen gas at 700 bars. When you do these types of advanced modeling calculations, we came to the conclusion that the solubility of the hydrogen in the crystal lattice structure, you expect a solubility of lower than 1 ppm. So still, a conclusion based on these modeling activities is that the hydrogen cannot penetrate through the polyamide crystals. It simply doesn't fit. That's one conclusion that we came up with. We also looked a bit into the solubility question. Why is the solubility of the hydrogen gas in polyamides pretty low? In order to answer that question, also we did some advanced modeling calculations. Here you see a computer box, you could say, where you mimic basically the amorphous polyamide chains. So you put polymer chains in this box and you allow the polymer chains to equilibrate. So the chains, they take the density, as you expect for the amorphous density of a polyamide. And what you do then basically is that you introduce in this system a single hydrogen molecule. You allow it, you just position it, you insert it in this computer box, and basically then you allow the polyamide material to equilibrate again in the presence of this hydrogen molecule. and then you can calculate. So basically you go from state A to state B, and you allow the system to equilibrate. And then also with this method, you can calculate the energy, the equilibrium energy that relates to the hydrogen molecule that is dissolved in this polyamide. Yeah? You need to do many calculations to get a kind of good average value for this energy. Yeah. Here you see an example, and you see the spread is pretty high. Here we performed 7 insertions of the hydrogen in the amorphous polyamide system. Yeah, and when we calculate then the amount, the average energy it takes to have this single hydrogen insertion, from this expression, you can calculate back the solubility based on this energy insertion. And then you end up that the solubility is something like 330 ppm. Yeah, and I showed you before that the experimental value was around 340 ppm. So this modeling approach, it's pretty accurate. Yeah, it can predict solubilities of hydrogen gas molecules quite accurately. Yeah, when you do the same calculation for solubility of oxygen, it's 5 times higher. And at the end, it has to do with the interaction level, the energetic interaction between hydrogen and oxygen. That explains basically this difference in solubility. And these modeling techniques are pretty powerful because we can now design polyamide materials by these computer models to have even lower solubility values for hydrogen. So these computer tools, these advanced modeling tools, we use to construct new or alternative polyamide structures that could lead to even lower solubility values and hence give lower permeation values. So this is an example where we use modeling expertise for material design. Okay. Well, during the years we have developed so-called fuel lock grades. That is the, let's say, the commercial name for these polyamide-based materials that we have developed for these tank applications. And I discussed you before, gas barrier is very important, but also we have to think about low temperature impact performance, that we have optimized over time. Also, ease of processing. We have developed fuel lock materials that can be blow molded into an inner liner, but also grades that can be injection molded. And our advantage of these fuel lock materials is that we have monolayer solutions. I mentioned before EVOH, that can also be used as barrier material for hydrogen, but you always have to combine it in a multi-layer fashion with polyethylene. And that's clearly an advantage when you think about ease of processing. Okay. Now, what does this mean in practice? I showed you these permeation values, but what does it really mean for a practical tank? Well, here you see an example of a tank geometry. This is the tank geometry that we take. The permeation requirement is 6 cc per hour per liter. So that's basically a permeation value expressed per volume. The permeability of this tank, you can imagine it directly scales with the area, which goes with 8p over r square, while the volume, that relates to r to the power 3. So this p over v value, it scales with 1 over r. That's what you see. Okay, and then you can use this information and this, let's say, this geometrical information to make estimates about what is now the permeation values that we expect for this tank geometry when we increase the volume of this tank. And here on the x-axis, you see the tank volume in liters, and on the y-axis, you see this permeation value in cc per liter per hour. The black line represents the hydrogen permeation spec, which is at a value of 6. Okay, the red line, yeah, that relates to the permeation value that you calculate as a function of the volume of the tank. Yeah, so what you learn from this graph is that for small volumes, smaller than 25 liters, you see that the permeation value is higher than the spec. Yeah, so we do not comply with the specification, but for larger tank volumes, 25 liters and more, we are compliant, as you can see. Yeah. So the conclusion is for practical tank volumes, yeah, 25 liters or more, yeah, we comply with the hydrogen permeation spec. And by the way, this is for a inner liner, yeah, that has a thickness of something like 2 millimeter, yeah, which is quite realistic. Yeah, so this means that for a tank volume of 120 liters, yeah, you are about a factor 2 lower compared to the specification. And this all has to do, of course, with the area to the volume ratio. Yeah? On the right-hand side, depicted by this elephant, the area to volume ratio is rather low, which is favorable. On the left side, you see the mouse. Yeah, the area to volume ratio is pretty high, yeah, and that is less favorable. Yeah? But the conclusion is for realistic tank volumes, based on fuel lock materials, we comply with the permeation values. Okay, here you see a bit the tank development over the years. So when you look at the early Type 4 tanks, yeah, their HDPE was used as an inner liner, and a thermoset was positioned at the outside. Yeah, and what you see is that now you see a gradual, let's say, change from HDPE to Aculon, fuel lock based materials, polyamide based materials. And then you see that you need less material, yeah, because the permeation value for polyamides is better, and you save weight. Yeah? That's one evolution that you see. Yeah? The next step will be that we move towards systems with the inner liner and this outside composite wrap that is now often based on a carbon fiber system with epoxy. Often the thermoset is an epoxy-based material. We as DSM think that over time, yeah, this epoxy will also be replaced by a thermoplast, for instance, a polyamide. So at the end, what we think is that for next generation Type 4 or Type 5 tanks, yeah, they will all be based thermoplast. And that links to the next development that I briefly want to show you. At DSM, we are also working on so-called UD tapes, unidirectional tapes, yeah, for these tank applications where we combine carbon fiber, so continuous carbon fibers, with polyamide-based matrix materials. Yeah. Well, the typical carbon fiber content is something like 40 to 50 weight%, and tape thickness is typically around 0.3 millimeters, as you see here. We are also working on recycle issues for these particular systems. And we are working on the grinding of these thermoplastic tanks. Okay? The advantage of these tanks is you can take them in again after life. Yeah? Then you can grind them, and then you can reuse them, yeah, in other applications. And here you see a demonstrator that we made, yeah, where you use, let's say, these grinded tanks again in other automotive applications. So that's another advantage. Besides weight reduction, yeah, you also have the possibility to recycle these full thermoplastic tank materials. When you need more information about this, please contact our commercial team at Engineering Materials at DSM. In view of the time, I also want to spend a few words on the fuel cell systems. Yeah, in a fuel cell, basically what you do is that you convert chemical energy of the hydrogen into electrical energy. Yeah. Here you see a single fuel cell stack where this happens. Yeah. Now, what do we think that we can contribute to fuel cell materials? There are two classes of applications that you can think of that are the so-called peripheral material applications, and that's currently now in our focus. And then you have to think about applications related to gas flow manifolds. Gas flow manifolds that are the devices that lead basically the gas stream to the fuel cell stack. Yeah, it's not in the fuel cell stack itself; it's still outside, so it's still a peripheral fuel cell application. We also think about humidifiers. We think about hydrogen supply systems like valves and tubes that could be made out of our polymer materials. Connectors, for instance. So there are several peripheral examples that we are investigating. When you think about the open challenges of a fuel cell, it relates to lifetime. We have contamination issues that lead to a lower lifetime of the fuel cells. That's an important thing. High cost, but also energy efficiency. These are the issues that relate to fuel cells. At the moment, for these peripheral applications, we mainly deal with contamination issues. Here you see an example of contamination issues. When you have, for instance, ions that enter into a fuel cell could lead to a performance loss because they block, for instance, the catalyst that is used, the platinum catalyst, and is not accessible anymore. Also, ions leakage can lead to pollution of the fuel cell. And at the moment, we are developing materials that could be used for peripheral applications. And that means that we minimize and reduce the amount of ions that leach from the plastic in the fuel cell. But these materials also need a very hydrolysis and chemical resistance. They should be dimensional stable. They should not lead to a drop in strength over time. And we are currently developing materials that, let's say, comply with these, let's say, requirements. I cannot say too much in this stage because there are still IP filings going on, so I cannot be too detailed about these fuel cell materials. Also, when you are interested in these types of peripheral fuel cell applications, please contact our commercial team at Engineering Materials at DSM. Okay, this was it basically. Let's come to some conclusions. I think I showed you that DSM is committed in providing solutions for hydrogen-powered cars in the future. A very nice example, I think, that we are committed to hydrogen economy is this example of February 2020, where DSM switched to green hydrogen for a vitamin B1 production in one of our production sites. This shows that we are committed to have this hydrogen economy in place. And I also showed you that we continue to invest in materials research and testing as an enabler for the transition to a safe, reliable, as well as economically viable hydrogen-based systems. Okay, I would like to thank you for your attention and see you next time. Goodbye.